So this is from the notes from last time, which I think I put these on Blackboard. Did I put these on Blackboard? So what you're doing here is we're trying to achieve gear train values or gear train ratios of greater than 10 to 1. A gearbox that will give us greater than 10 to 1 ratio. The way to achieve that is through compound gears. Compound gears are gear sets where at least one shaft has 2 gears on it, a compound number of gears. And so on this one here, this shaft right here is carrying gear 3 and 4 simultaneously. It's rotating at the same speed. So omega 3 equals omega 4, which equals omega 3 4. And we have one meshing here and one meshing here. Before we saw that if we just concatenate a bunch of gears all in a row, that the gear train value doesn't change because we just got a series of idler gears that are just changing the gear train's value of the direction. But in this one here, when we cross this out here, we still have N2 over N3, N4 over N5. And so that's what we're trying to achieve on that. All right? Let's go ahead and, so are there any questions on this before we do a problem using this technique? Okay, so on this, I believe
The goal is 10 to 1. Is that the goal?
the goal is to never exceed a 10 to 1 ratio on a single mesh. And so how do we get these ratios of, say, 250 to 1? And that is, the answer is using compound gears. All right. So I believe this problem that I'm about to do, because I don't have the book with me, I believe this problem, here's a second, Monday. This is very similar to how you're going to be doing the problem that you have on your homework that's due on Wednesday, the last problem number 3 that we're discussing. So on this one right here, what we're trying to achieve is a gear train value, overall gear train value of 50 to 1. And we have a diametral pitch of 8 T. So let's just write out what we're trying to achieve here. The overall gear train value is to be minus N2 over N3 minus N4 over N5. We want that to equal 1 over 50. Okay? So there's a couple ways to do these problems. What you do is you look at the overall gear train value, which is 50, and you do what I call a least factors approach. So this is 2 times 5 times 5. All right, so that's the least factors approach. So that means that we can go ahead and do a 2 to 1 and a 25 to 1. Can we do that?
No.
Now why?
Yes.
Too big. So we can't do that. But we could do a 10 to 1 and a 5 to 1. So right here, we're right on the threshold of our maximum, but we're allowed to still do it. All right? So we can do a 10 to 1 and a 5 to 1. The other approach is called the square root or cubed root or quad root of the number, depending on how big that number is. So if I do the square root of this here, I get 7.07 I can round that up to 8. And so I can use an 8 to 1 and then a 6.25 to 1. Now this fractional gear train value, 6.25 to 1, could be a problem, but since it's 6 1/4, I think I could probably get around that because 6 1/4 times 4, I have the whole number there. All right, so because what we're trying to do, not trying to do, we have to do is we can't have fractional tooth counts. And so whenever I'm dealing with a fractional gear train value, it kind of scares me a little bit, but in this case here, because it's such a nice fractional value being 1/4, I think I can get away with that, okay? So let's go ahead and think about that for a second. And then the other one is if I take that number there and round down to 7, and then this right here, 7 to 1, and then 7.1428 to 1. Now this one here really, I'm a little concerned about because it's such an odd looking fractional number. But let me just deal with that later and see what my result is, all right? The reason I like doing the square root approach or the cube root approach if the number is very big is because the gear train value or the overall assembly size of it is pretty compact, okay? So because it's compact, we don't have to build a big box around it. It keeps it pretty tight. So let's do A first. So A is 10 to 1 and a 5 to 1. So I do N2 over N3 equals 1 over 10. And I also, well, okay, so let me just finish this. So because it's 10 to 1 according to that table, and I don't remember that table number.
Let's do the big reference.
What is it, 9?
9.58.
So looking at that table, which we're going to use that table on all these problems that we do using gears, that means that my N2, I have to use at least 17 teeth. So that means that N3 equals 170 teeth because it's 10 to 1, so 10 times 17 is 170. And D2 equals 2.125 inches. And I get that because I know that my diametral pitch is 8 teeth per inch. So I take 17 divided by 8, and that equals 2.125 inches. And that's the diameter back here. And then the diameter of 3 equals 21.25 inches. All right. And then my N4 over N5 equals 1 over 5. So that means because it's 5, I can actually use a smaller pinion. According to that table, I can use 16 teeth. And that means that N5 equals 16 times 5 is 80 teeth. And the goal on using smaller or tooth counts less than as small as possible is generally they cost less to purchase. All right. So we're trying to reduce or keep the tooth count as small as possible because of cost. So 16 divided by 8, D4 equals 2 inches, and D5 equals 10 inches. All right?
Sorry, why are you dividing by 8?
Because that's the diametral pitch given in the constant. Great piece of D, top right. Okay.
So does it matter if you do N2 and 3, the 1 and 5?
No.
That doesn't matter.
It So the question is, could I have had n2 over n3 equals 1 over 5, n4 over n5 equal 1 over 10? Yes. But the one thing that you need to be aware of here is that you want a positive ratio F. So you need to look at the number of gear meshings. So a positive ratio implies an even number of meshings. Whereas a negative ratio implies an odd number of meshings.
But that only applies to when it's over 10.
It even applies when it's less than 10.
Because on problem 1 for them, it's -9 to 1, but they still need 2 gears.
One meshing. One is an odd number, right?
So where the forces, okay.
Okay. All right. So with this here, so if I have 2.125, let me just use ratio 1/2 here. This is to scale, so I mean, you can scale it any way you wish here. Scale up or down, or use the same ratio. So then this one here, this is 21.5, so that goes 21.5 here. So this is N2. This is N3. And then on this one here, I have 2. So this is N4. Then I have 5, which is, that's 10 spots. If I look at the overall size here, I'm getting at this. All right. So if this is rotating in a positive fashion, this is rotating in a negative fashion, and this is rotating in a positive fashion. So that gets us that plus 50 to 1 ratio out of that. And then if I look at the overall dimensions here, when I measure that, I get D2 plus D3 equals 23.375. So that would be the size of the housing that has to go around that thing, if I was to put a housing around it. At least that it has to be, of course, it has to allow for clearance, so probably 24 inches or something like that. Okay? All right, so that's A. Let's do B now.
Sorry.
Yeah, go ahead.
How did you, okay, so once you had the numbers for the diameter, how did you place all of those?
So what I did was, this one right here is D2, 2.125 inches. This here is D3, so this is 21.25 inches. This one here is 4, so that right there is 2 inches. And this is 5, so that one there is 10 inches.
No, I get that, but like, why the placing of them though? Like, why is N4 placed below N3?
I mean, I could have done it on, so
But why is it not next to it? Like, how
I
did you
could have
know?
gone like that.
Yeah,
And
but,
I could also have taken this and put it over here,
why is it not all in a row? Like,
because it has to be a compound gear. The point of doing this exercise is to make sure that at least one shaft has 2 gears on it in order
so
to
how
get that.
did you know which gears to make those choose?
You know that from joining this gear here, the big one, with the small one.
So it always is going to be between 3 and 4?
Always between 3 and 4, always between 5 and 6, always between 7 and 8, and so on.
Okay.
Does the size of N4 with respect to N2 matter?
N4 with respect to N2, well,
As long as it's the same relationship with N5?
you need to, the size of N4 and N5 are directly coupled together.
Right.
The size of N2 and N3 are directly coupled together. Combining those two numbers has to be 50 to 1. All right? What else?
How did you get the positive and the negative?
So if this is moving in a positive fashion, this one here is moving in a negative fashion. Since this shaft is welded to 3 and 4, this is moving in a negative fashion.
So this is a top view?
This is a top view, yeah.
Okay.
All right.
Did you just put N4 right in the middle and 3?
N4 is this one right here.
Yeah, did you just weld it right in the middle of N3?
Yeah, this shaft here has to be in the center of this gear. This shaft here, which is the same shaft, has to be in the center of that gear.
All right, this might be a silly question, but since you said these have 4 meshings, I'm like, will you count the 4, because I count 3?
There's only 2 on this one here. There's a meshing between
Okay.
2 and 3. There's a meshing between 4 and 5. All
Okay, so you don't count the intermediate.
right. So think of these things as pitch points. So you got a pitch point here, P, and a pitch point here, Q. 1, 2, P and Q, you have an even number of meshings, gives you that positive output. What else on this?
Can you explain again from where you get 10 to 1, 5 to 1?
At 50, break it into the least factors, 2 times 5 times 5. So I get 10 to 1 and 5 to 1. All right, you ready for B? So you would have to do a side view of this too. All right, so your side view would be here. Okay.
Will you spell that up?
What's
Speed
that?
that up.
All right. So on B, I said we're using an 8 to 1 and a 6.2